All right, so we're looking at bonding 2. This is part 1. We're going to start looking at covalent bonds a little bit more, molecular shapes, network solids. This is kind of going to be a little rehash of one of the POGLs that we did earlier. So, covalent bonding. We know that covalent bonding is sharing. Sharing is caring. Covalent bonds like to share. There's nonmetal, nonmetal. All right, so the covalent bond, we already know, nonmetal, nonmetal, it's sharing, formed between elements with an electronegativity difference less than 1.7. So if it's over 1.7, ionic. Less than 1.7, covalent. Since nonmetals are 1, 2, 3 electrons shy of an octet and have high electronegativity values, nonmetals will not tend to give up their electrons. They don't want to, so they want to share. That's the only thing they have left is sharing. So to complete, let me move me out of the way. To complete the octet, that makes everybody happy, and hold on to all of its electrons that it already has, a nonmetal will share with another nonmetal. The bond forms as both nuclei pull on the shared pair, so they're like holding it together. There's no take, it's sharing. Sharing electrons belongs to both atoms and are counted as the octet for each, on each. So this will count 8 over here, and this will count 8 over here, using both as perfectly like this as a Venn diagram. Both are shared in between. All right, this I think was at one point time supposed to move together, so this would move with that, making 8, but it doesn't anymore. All right, so molecular properties, they combine nonmetals with nonmetals. They're shared, and they're molecular. It's not like what we were looking with ionic. Ionics, you see solids and they're lattice structures put together, and we want to get empirical formulas. Now we have molecular, where you just have molecules together, not a huge repetitive, all of them all together. So in this, these substances are not conductive because they're nonmetals, nonmetal. Molecular substances have low melting points and low boiling points. Many are liquids and gases. And any of the solids you have are super, super soft, like gallium. Gallium basically melts in your hand. Okay. Formulas: molecular, empirical, and structural. So molecular formula C6H12O6 represents the individual molecule, where its empirical formula is the simplest ratio. The structural formula, however, provides the most information. So looking at this, we'll get to this when we get to organic. Don't stress too much. You're not really going to see this very much, but you see how it's all put together and how everything is bound together, sharing. And the term molecule implies a structure with a covalent bonding. Drawing the electron dot diagrams, the electron structures, one of my favorites. So again, you add up all the valence shell electrons. You write the symbols showing the arrangements using single bonds. Complete the octet of the attached atoms. Place the remaining electrons on a central atom. If there are not enough electrons to form an octet on the central atom, try multiple bonds like a double or a triple bond. All right, so PCl3 or potassium chloride. So we're looking at this, and you're going to look at this some of the electrons. So in potassium, you have 5 electrons in the valence shell, and chlorine has 7, but there's only 1 potassium, so there's 5, and there are 3 chlorines. So 3 times 7, 21. 21 and 25 is 26. So there are 26 total electrons, meaning 13 pairs. Just divide it in half because 2 divided by 2, works. Write the symbols and complete the single connections. Complete the octet and place all the remaining electrons in the central atom. So there's 13 pairs. So first, sorry, that looks really, really horrible. So I would put one up here, one over here, one over here, one over here, right? All 5, like get my 5 in there. And then I'm just going to add the other ones around. And I'm so sorry, this looks horrible. Basically, it shows that it all works out together where one pair goes on top. That is horrible. I'm so sorry for that. This is what it should look like, all right? So you're going to check the octet. And so you do the inside first, the connecting ones. So 1, 2, 3, 4, 5, 6. Then you do 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And that's what you get. All the octets are formed. Check the formula charges again. So this does 5 minus 2 plus half of 6. 2 plus half of 6 is 5. That equals 0. There's 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 6. I'm trying to think of how that works out. Don't worry, we'll figure this out in class. It's not horrible. Oh, 6 around. Sorry, that's what it meant. So 1, 2, 3, 4, 5, 6. So there's 6 around. Half of that, half of 2, and it gives you 7. You're good. All right, let's look at some water, hydrogen oxide, dioxide, or I lost it. Dihydrogen oxide. There you go. So hydrogen, there's only one valence shell, one electron in the valence shell, and there's 2 of them. So 1 times 2 is 2. Oxygen is going to have 6. So there's 1 of those times 6. Altogether, you're going to have 8 electrons, or 4 pairs. So what you're going to do with this, come on, you're going to put a hydrogen and an oxygen, and you're going to want another hydrogen. So there are 2 pairs that go right here, 2 pairs that go right here. Sorry, the dots got moved. So there should be 1 here, 1 here. That's 2, 4, and then I'm just going to go around the rest of the way around the oxygen. So 2, 4, 6, 8, and that matches up. All right, so the exercise, I don't have the answers to here. You're going to give me the Lewis dot for each. Draw the electron dot structures for each of the following. What is the central atom? How many negative regions are surrounding it? How many of the regions are bonding sites and non-bonding? We will go over these in class. Pardon me. If you have any questions, please don't hesitate to ask. And I hope you guys have a great day.